Hello everyone and welcome back to the BrainOmega channel. Today we have another tutorial and hands-on session for you, and we're tackling one of the most critical topics in artificial intelligence, LLM alignment. We'll explore exactly how developers take a powerful but raw AI and carefully shape it to be helpful, honest, and safe for users. Have you ever stopped to think about the magic behind an AI like ChatGPT? You ask it a complex question, and it doesn't just spew out random text from the internet. It understands your intent, it adopts the right tone, it tries to be helpful. How did a machine learn to be so cooperative? The journey from a raw, chaotic language model to a helpful assistant is not an accident. It's the result of a deliberate and ingenious process called alignment. Today, we're taking a deep dive into this process. Using this seminal diagram from OpenAI's research on InstructGPT, the model that paved the way for ChatGPT, we'll explore the science of teaching an AI to share our goals. We will break down each step in detail, understand why alignment is arguably the most important problem in AI safety, and examine the significant challenges that still have researchers racing to find better solutions. This is the story of how we're trying to make sure AI works for us, not just near us. Let's get started. Imagine a brilliant student who has read every book in the library. They have all the knowledge, but they're unfocused, they ramble, and they don't know how to answer a direct question. That's a base language model like the original GPT-3. Its only training was to predict the next word on a massive scale. The alignment process is how you turn that brilliant but unfocused student into a dedicated, helpful research assistant. The core technique is reinforcement learning from human feedback, or RLHF, and it begins with step 1, supervised fine-tuning SFT. The goal here is to give the model a basic template for what a good answer looks like. The process starts with collecting real-world prompts, many of which came from actual users of OpenAI's early API. This is crucial. It's not just academic questions, but messy, real-life requests. For our example, the prompt is, explain the moon landing to a 6-year-old. Instead of letting the AI try to answer, a human expert, a labeler, steps in and writes a high-quality exemplary response. You see it here. Some people went to the moon. This is called demonstration data because it demonstrates the desired behavior. This curated data set containing thousands of these prompt demonstration pairs is then used to fine-tune the base model. Think of it like a chef's training. You don't just give them a cookbook. You show them videos of a master chef preparing each dish perfectly. They learn the right techniques, the right timing, and the right presentation. This step alone provides a massive improvement, but SFT has a weakness. You can't possibly create a human demonstration for every single type of question a user might ask. To get an AI that can generalize to new, unseen prompts, we need to move from learning by imitation to learning from preference. That brings us to step 2, training a reward model. This is where we build our AI judge. The objective here is to teach a separate AI to understand human preferences with nuance. We start with a prompt and have our SFT model from step 1 generate several different answers. Here, A, B, C, and D. Let's imagine what these could be. Answer A might be technically correct, but full of jargon about orbital mechanics. Answer B might be factually wrong, saying they flew there in a balloon. Answer C might be simple, accurate, and engaging for a child. Answer D might be a bit too simplistic, leaving out key details. A human labeler then ranks these outputs. It's often much easier for a person to compare and say, C is better than A, which is better than D, which is better than B, than it is to write the perfect answer C from scratch. This ranking, D is preferred over C, which is preferred over A, and so on, is the crucial piece of data. Thousands upon thousands of these comparisons are collected and used to train a completely separate model. the reward model, RM. This reward model becomes our automated judge. It doesn't know how to write a story about frogs itself, but after reviewing countless ranked examples, it develops an incredibly sophisticated sense of what humans find helpful, truthful, and well-written. It learns to assign a high score to good answers and a low score to bad ones. Now that we have our judge, we can use it to train our main AI at a massive scale. And this leads to the grand finale, step 3, reinforcement learning. This is where the magic truly happens, in a dynamic and continuous loop. A new prompt is sampled, like write a story about frogs. Our main AI, the policy, writes an answer. Instantly, the reward model we just trained swings into action. It reads the prompt and the AI story and outputs a single number, a reward score. A high score says, great job. A low score says, try again. This reward is then used to update the AI's policy using an algorithm called PPO, or Proximal Policy Optimization. In simple terms, PPO is a clever way of taking a small, stable step in the right direction. It encourages the model to try things that will get a higher reward, but it does so cautiously, ensuring the model doesn't drastically change its strategy and forget all the useful language skills it already has. This loop runs millions of times. Generate, score, update, generate, score, update. The AI is essentially in a high-speed training simulation, constantly refining its ability to produce outputs that our AI judge and, by extension, humans will like. However, this intense optimization comes with a risk mentioned in the article, the alignment tax. If you only train the AI on pleasing the reward model for user tasks, it can start to forget some of its core knowledge and perform worse on other academic benchmarks. To solve this, OpenAI mixes a small amount of its original pre-training data back into this step. It's like making a student study for a specific exam, but also ensuring they keep up with their regular coursework so they remain well-rounded. As powerful as RLHF is, it is not a silver bullet. It's the first major step, but it comes with serious limitations that define the cutting edge of AI safety research today. First, as we've noted, it's incredibly resource-intensive. It relies on a human-in-the-loop system, but that loop is a bottleneck. We can build bigger models far faster than we can generate the high-quality human data needed to align them. Second, and perhaps most critically, is the problem of bias. The AI is being aligned to the preferences of a few hundred to a few thousand labelers. This group cannot represent the full diversity of global cultures, values, and perspectives. If you ask about a beautiful home, whose definition of beauty does it use? If you ask about a fair political policy, whose definition of fairness gets encoded? This is a profound societal challenge. Third, there is the risk of reward hacking. The AI's goal is simply to maximize its score from the reward model. It might discover that it can trick the judge. For instance, it might learn that long, confident-sounding answers get high scores, so it generates verbose, jargon-filled text that seems impressive but is actually vague and unhelpful. It's optimizing for the appearance of being good, not the reality. Because of these challenges, researchers are actively developing what comes next. This includes concepts like constitutional AI, where an AI critiques and improves its own answers based on a written constitution of ethical principles, reducing the need for constant human oversight. Other methods involve using AI models to debate each other to find flaws in reasoning, creating a more robust alignment signal than any single human could provide. The holy grail is to discover an alignment technique that scales with a model's intelligence, ensuring that as AI becomes ever more powerful, our ability to wisely steer it grows right alongside it. And for those who want to dive into the practical side, The complete code for this project is available on our GitHub page. You can access the link in the description of this video. Today, we are going to explore one of the most recent and powerful alignment algorithms, ORPO. The complexity of RLHF led researchers to ask, can we achieve the same goal more directly? This led to the breakthrough of direct preference optimization. The complexity of RLHF led researchers to ask, can we achieve the same goal more directly? This led to the breakthrough of direct policy optimization, or DPO. The core idea of DPO is brilliant. It showed that the entire complex RLHF pipeline can be mathematically simplified down to a simple loss function. All you need is a preference dataset with triplets of a prompt, a chosen response that is preferred, and a rejected response that is not. The DPO loss function then directly optimizes the model to assign a higher probability to the chosen response and a lower probability to the rejected response for the same prompt. This is much more stable and simpler than RLHF. However, DPO still has one drawback. During training, it needs to constantly compare the fine-tuned model's probabilities to the probabilities assigned by a frozen reference copy of the original model. This reference model consumes a significant amount of extra GPU memory. This brings us to the cutting-edge algorithm we'll be using today, ORPO, which stands for Monolithic Preference Optimization. ORPO's big idea is to ask, what if we could combine the simple SFT objective of learning to say the right thing with the DPO objective of learning to prefer the right thing into a single, elegant loss function? And that's exactly what it does. The ORPO loss has two parts. The first part is the standard next token prediction loss on the chosen response, just like in SFT. But it adds a penalty term. If the model assigns a very low probability to the good chosen response, it gets a large penalty. This forces the model to first learn to generate the good response well. Then, the DPO-like part of the loss kicks in to push the probability of the chosen response even higher than that of the rejected response. The incredible result of this combined approach is that it eliminates the need for a separate reference model. Because we're simultaneously reinforcing the correct language and the preference, the model doesn't drift away from its core knowledge. This makes ORPO even simpler and more memory efficient than DPO. It's the state of the art, and it's what we are going to build. So, you want to run the ORPO Llama fine-tuner project but don't have a powerful local GPU? No problem. We'll get it running in minutes using Google Colab. First, let's make sure our environment has the necessary hardware. Go to Runtime, select Change Runtime Type, and in the Hardware Accelerator drop-down, choose the T4 GPU. This is the key step that gives us the power needed for fine-tuning. Click Save. Now, let's bring in the code. In the first cell, we'll use the exclamation mark git clone command followed by the project's GitHub URL. When you run this, Colab will download the entire ORPO Llama Fine-Tuner repository into our workspace. Next, we need to navigate into the project folder that was just created. We'll use the command %cd orpo-llama-fine-tuner. The %cd command changes our current directory so we can run the project's scripts. Finally, you're ready to start the fine-tuning. Simply run the command !python main.py. Colab will now execute the main script using the free T4 GPU to handle the intensive training process, and that's it. You're now successfully running the ORPO Llama Fine-Tuner project in the cloud. We will walk you through the process of setting up access to our dataset and model. The first step is to create a new Google Cloud project and configure an OAuth client. On the screen, you'll see a Google Drive access page. If you're trying to access to dataset or model, you might encounter this page requesting access. Simply enter a message if you like and click Request Access. We will then approve your request. Meanwhile, to get started with the necessary credentials, open your Google Cloud Console. If you don't have a project yet, you'll need to create one. Click on New Project and fill in the details. Once your project is created, navigate to the Client section. If you see a message that says Google Auth platform not configured, don't worry. Click on Create OAuth Client. This will take you to the setup process for your credentials. This is a crucial step for authenticating your application's access to Google Cloud Services. This process ensures secure access and management of your data and models. By following these steps, you'll have the foundational setup needed to move on to the next phase of our tutorial. Continuing from our last step, we are now ready to create the OAuth client ID that will be used to access our dataset and model. In your Google Cloud Console, under the Clients section, click on Create OAuth Client ID. You will be presented with a form. Select Web Application. As the application type, give your client a name. Something like Model Access is a good example. You don't need to fill in the authorized JavaScript origins or authorized redirect URIs for this particular setup. Click Create. Google will then generate your OAuth client credentials. A pop-up window will appear showing your client ID and client secret. This is your authentication key. Now, let's look at the file structure on the right side of the screen. You should have a folder for your project, in this case, ORPO Llama Fine Tuner. Inside, you'll see files like config.py, main.py, and trainer.py. To properly configure your access, you need to create a file named credentials.json. Take the JSON snippet that Google provided and save it as credentials.json inside your project folder. The arrows on the screen show the file being renamed to credentials.json and being placed in the root of your project folder. This file will be read by your application to authenticate with Google Cloud Services, allowing you to seamlessly access your dataset and model for your fine-tuning tasks. This finalizes the setup for authenticated access. All right, with that deep dive into the theory, let's open up the code and start building. We're in the model/llama.py file. This single file will contain our entire from-scratch implementation of the Llama model architecture. First, let's walk through the imports at the top so we know what tools we have at our disposal. Import math. This is a standard Python library we'll need for just one thing, a square root calculation inside our attention mechanism. From data classes, import data class. This is a modern Python feature that gives us a super clean way to create classes that are primarily used for storing data, like our model configuration. From typing import optional, tuple, these are for type hinting. They don't change how the code runs, but they make it much more readable for us and other developers by specifying what kind of data to expect. Import torch, import torch.nn as nn, and from torch.nn, import functional as f. These are our workhorses. We're importing the main PyTorch library, its core neural network module class, which we'll inherit from, and the library of common functions like softmax and silu, which we'll use by the conventional alias f. With our tools imported, we define our model args data class. Think of this as the blueprint or the recipe for our Llama model. It holds all the key architectural parameters in one organized place. Dim is the core dimensionality of our model's embeddings. Layers defines how deep our transformer will be. Heads is the number of attention heads. Cave heads is a key parameter for an optimization called grouped query attention, which we'll explore in detail. Vocab size defines how many unique tokens our model understands. And norm EPS is a tiny number we'll add during normalization to prevent any division by zero errors. This data class is our single source of truth for the model's architecture. The first component of our Llama model is its normalization layer. Instead of the standard layer norm used in the original transformer, Llama uses a simpler and more efficient variant called RMSNorm, or root mean square normalization. Let's look at the init method. The key thing you'll notice is that it only has one trainable parameter, self.weight. This gain vector allows the layer to scale the normalized output. Unlike layer norm, there is no bias or shift parameter, which is part of what makes it simpler. The core logic is in the norm function. The formula for RMSNorm is to take the input vector x and divide it by the square root of the mean of the squares of its elements. The x.pow of 2.mean over minus 1, keep dim equals true part, calculates the mean of the squares. Torch.rsqrt is a highly optimized function that calculates 1 over the square root, which is faster than doing torch.sqrt and then a division. The small eps value is added for numerical stability to prevent division by 0. In the forward pass, we first normalize the input x by calling our underscore norm function. Then, we take this normalized output and multiply it by our learned weight parameter. This allows the network to learn the appropriate scale for the features at that point in the model. It's a simple, fast, and effective normalization technique. Next, we come to one of the most important and clever innovations in modern transformers: how we handle positional information. The original transformer added a separate, learned positional embedding to the token embedding. Llama uses a more advanced technique called rotary positional embeddings, or ROPE. The core intuition behind ROPE is that instead of adding position information, we can rotate our query and key vectors in a way that encodes their absolute and relative positions. The amount of rotation depends on the token's position in the sequence. Because the dot product between two rotated vectors depends on the difference in their rotation angles, the attention mechanism naturally learns to favor tokens with a certain relative distance. Let's look at the code. The pre-compute effects CS function does exactly what its name says. It pre-calculates the cosine and sine components of all the rotation angles we will ever need, up to our max sequence length. It first calculates a set of base frequencies that are different for each dimension of our vectors. Then, it uses torch outer to create a matrix where each row corresponds to a position in the sequence and each column corresponds to a feature dimension containing the precise angle for that position dimension pair. The apply rotary MB function then takes our query and key vectors, xq and xk, and applies these rotations. The math looks a bit complex, but it's just a 2D rotation formula. It treats each pair of features in our vectors as a single complex number and multiplies it by the pre-computed rotation angle. This elegant method has been shown to be incredibly effective at helping transformers understand the relative positions of tokens. Another major innovation in the Llama architecture is an optimization called Grouped Query Attention, or GQA. Let's first understand the problem it solves. During inference, when the model generates text token by token, it stores the calculated keys and values from all previous tokens in a key value cache to avoid recomputing them. In standard multi-head attention, you have a separate key and value head for every query head. This cache can become a huge memory bottleneck. To solve this, a technique called multi-query attention was proposed, where you have many query heads but only a single key and value head that is shared by everyone. This drastically reduces the size of the KV cache but can sometimes lead to a loss in quality. Grouped query attention is the perfect compromise. We have our full number of query heads, but we have a smaller, intermediate number of key and value heads. These KV heads are then shared across groups of query heads. For example, we might have 32 query heads, but only 8 KV heads, where each KV head is shared by a group of 4 query heads. The repeat KV function is the simple but essential mechanism that implements this sharing. It takes the key or value tensor, which has the smaller number of n KV heads, and it skillfully expands and reshapes it to match the full number of query heads. This effectively copies the KV heads so that each group of query heads can attend to its designated shared key and value. Alright, let's assemble all these advanced components into our main attention module. In the init method, we first calculate all our head dimensions based on the model args. We define our 4 crucial linear layers, WQ, WK, and WV, to project the input into query, key, and value vectors, and WO for the final output projection. Then we have a very important check. We see if our PyTorch version has scaled dot product attention. This is the function for flash attention, a highly optimized implementation of the attention mechanism that is much faster and more memory efficient. If it's not available, we fall back to creating a manual causal attention mask. Now for the forward pass, let's trace the data flow. The input X comes in. First, we pass it through our WQ, WK, and WV layers, and then reshape the output to separate the heads. Notice XK and XV are reshaped with the smaller N local KV heads. Next, we apply our rotary positional embeddings to the query and key vectors, rotating them to inject the positional information. Then we call our repeat KV function to implement grouped query attention, expanding the key and value tensors to match the number of query heads. After transposing the tensors to prepare for matrix multiplication, we finally calculate the attention. If flash attention is available, we use the single, highly optimized scale dot product attention function, simply setting is causal equals true. If not, we perform the manual attention calculation. Matrix multiply, Q and K transposed, scale, add the mask, apply softmax, and multiply by V. Finally, we reshape the output tensor back and pass it through our final output projection layer, WO, to get the result of this attention block. Every transformer block has 2 main components, an attention sublayer and a feed-forward sublayer. We've just built our advanced attention module. Now let's build the feed-forward part. The Llama architecture uses a specific variant of a feed-forward network called SWI-glue. In the feed-forward class, you'll notice it has 3 weight matrices, W1, W2, and W3. The forward method implements the SWI-glue formula. The input X is projected up by 2 separate matrices, W1 and W3. The output of the W1 projection is passed through a SILU activation function, which is then multiplied element-wise with the output of the W3 projection. This result is then projected back down by the W2 matrix. This gated structure has been shown to be very effective. Now we can finally assemble our complete transformer block. In its init, it simply creates an instance of our attention module and our feed-forward module. It also creates 2 separate RMSNorm layers, one for each sublayer. The forward pass clearly shows the modern pre-normalization structure. The input X is first normalized by attention norm before it goes into the attention module. The output of the attention is then added back to the original unnormalized X in a residual connection. This result, H, is then normalized again by FFNorm before it goes into the feed-forward network. And finally, that output is added back to H in a second residual connection. This norm, then transform, then add pattern is a key feature of the Llama architecture and is critical for stable training of very deep networks. We've built all the components and now it's time for the final assembly in our Llama class. In the init method, we put all the pieces together. We create our TOC embeddings layer, which will map our input token IDs to dense vectors. We then create our stack of transformer blocks, using a module list to hold all n layers of them. After the blocks, we have our final norm layer and the output linear layer that will produce our final vocabulary scores, or logits. Finally, we call our precompute freq CIS function one time to calculate our rope frequencies, and we register them as non-persistent buffers. This is a small optimization that tells PyTorch these tensors are part of the model's state, but don't need to be saved in the state direct, as they can always be recomputed. Now for the forward pass. It takes our input tokens and optional targets. First, it gets the token embeddings. Then, it slices our pre-computed ρPE frequencies to match the current sequence length. It then passes the embeddings through every single transformer block in a for loop. After the final block, it applies the final normalization. Now we have a conditional check. If targets are provided, it means we are in training mode. We calculate the logits for the entire sequence. We then perform a crucial shift. We shift the logits one position to the left and the targets one position to the right. This aligns the prediction at time step t with the target at time step t plus 1, which is exactly the next token prediction task. We then calculate the cross-entropy loss. If targets are not provided, it means we are in inference mode. We don't need to compute logits for the whole sequence. We only care about predicting the next token. So as an optimization, we only compute the output for the very last token in the sequence, which is much faster. Let's take a quick look at config.py. This is our project's control panel. We've defined all our important parameters here. This includes training parameters like the batch size, epochs, and learning rate. A key parameter for our specific fine-tuning task is alpha ORPO. This is the scaling coefficient, often called lambda, that balances the two parts of the ORPO loss function, the standard language modeling loss and the preference ranking loss. The value of this parameter can have a significant impact on the final performance of our fine-tuned model. We also have our system and path configurations, which tell the script where to find the tokenizer, where to save checkpoints, and which dataset to use from the Hugging Face Hub. Having all of these settings in one place makes our code much cleaner and our experiments much easier to manage. Our project is designed to start from a pre-trained model, which we need to download. The script utils/gdrive.py is a self-contained utility for handling this. The getDrive service function is responsible for authenticating with the Google Drive API. It uses the standard OAuth2 flow. The first time you run it, it will look for a credentials.json file, which you need to get from the Google Cloud Console. It will then prompt you to visit a URL in your browser, authorize the application, and paste back an authorization code. Upon success, it saves your credentials in a token.json file. On all subsequent runs, it will find this token.json file and reuse your credentials without asking you to authorize again. The download and extract zip function then uses this authenticated service to download the specified file from Google Drive. It downloads the file into an in-memory buffer, shows the download progress, and then uses Python's zip file library to extract the contents, our model and tokenizer, into the correct directory. This makes the initial setup of our project completely automated. Now we arrive at the main conductor of our project, the ORPO trainer class in trainer.py. This class encapsulates all the logic for our fine-tuning process, making our main script incredibly clean and simple. Let's look at the init method. It acts as a master setup function. Instead of having one giant, messy constructor, we've broken down the setup process into a series of logical private helper methods. It first sets up our weights and biases logging, then it sets up the tokenizer, then it loads and prepares our Llama model, then it prepares our data loaders, and finally, it sets up our optimizer and learning rate scheduler. We're going to walk through each of these setup methods one by one to see exactly what they do. Let's look at the setup methods inside our ORPO trainer. First, setup port tokenizer calls our Google Drive download utility to ensure the files are present. Then it uses auto-tokenizer from pre-trained to load our tokenizer from the local path. It then configures the tokenizer with the specific chat template and pad token that the model expects. Next, Setup model is where we load our pre-trained weights. It loads the base.pt checkpoint file, which contains both the model's configuration and its weights. It intelligently uses the model config from the checkpoint to create an instance of our from-scratch Llama class with the exact same architecture. Then it calls model.loadStateDictionary CKPT to load the pre-trained weights into our model. This is a perfect example of how to separate a model's architecture from its trained weights. Finally, here prepare data loaders handles our dataset. It's a smart function that first checks if we have a pre-processed tokenized version of the dataset saved locally in a cache. If so, it loads it instantly. If not, it downloads the raw dataset from the Hugging Face hub, performs all the necessary filtering and pre-processing steps to get it into the format we need for ORPO, and then saves the result to the cache directory, so we never have to do this slow pre-processing step again. It then creates and returns our standard PyTorch data loaders for training and validation. Now for the mathematical core of our trainer. The setup optimizer function creates our AtomW optimizer, which will update our model's weights. We also define a custom learning rate scheduler. This scheduler will implement a warm-up phase, where the learning rate gradually increases from 0, followed by a cosine decay phase, where it smoothly decreases. This is a very common and effective schedule for training transformers. The calculate log probs function is a complex but necessary helper. Its job is to calculate the total log probability of just the response part of a sequence, ignoring the prompt part. It does this with some clever masking. Finally, the get ORPO loss function. This is the heart of the entire project. It takes a batch of data and first performs a forward pass with the positive input IDs to get loss pos, which is our standard SFT language modeling loss on the chosen response. It then uses our helper function to get the log probability of this chosen response. It does the same for the negative input IDs to get the log probability of the rejected response. It then calculates the log odds term. This formula, taken directly from the ORPO paper, represents the odds ratio between the chosen and rejected responses. This term is then passed through a log sigmoid function. The final total loss is the combination we discussed in our theory section. It's the standard SFT loss, loss pos, minus our preference loss term, scaled by alpha ORPO. This is the single value we will backpropagate to train our model. With all of our setup methods and our loss function defined, the final train method is the orchestrator that puts them all into action. It starts by printing a banner and getting an initial estimate of the loss before any training has happened. This gives us a good baseline. Then it enters the main for loop, which iterates over our desired number of epochs. Inside this, we have another loop that iterates through every single batch in our train loader, wrapped in TQDM to give us a nice progress bar. For each batch, we perform the standard PyTorch training steps. We call optimizer.0grad to reset the gradients from the previous step. We move the batch of data to our target device, like the GPU. We call our getORPOLoss function to perform the forward pass and compute our final loss for this batch. This is the learning step. Total loss.backward computes the gradients. clipgrad.norm is a standard technique to prevent gradients from exploding. And optimizer.step and scheduler. Step, update our model's weights and the learning rate, respectively. Periodically, based on our log interval, we pause to call our estimate loss function, which evaluates the model on both the training and validation sets, and we log these metrics to the console and to weights and biases. Finally, at the end of every epoch, we call save-checkpoint to save our model's progress. The entire loop is wrapped in a try. Finally blocked to ensure that even if we interrupt the training, our resources are cleaned up properly. Last but not least, let's look at main.py. After all the complexity we've built in our model and trainer files, our main entry point is beautifully simple. This is a sign of a well-designed modular codebase. At the top, we have a place for you to insert your Hugging Face API token. We also enable some PyTorch performance enhancements like allow TF32, which can speed up computation on modern NVIDIA GPUs. Then we import our ORPO trainer class. The main function itself is incredibly concise. It does just two things. First, it creates an instance of our ORPO trainer. As we know, the __init method of this class will trigger our entire setup process, downloading data, loading the model, and preparing the optimizer. Second, it calls trainer.train, which kicks off the main training loop we just reviewed. The standard main block ensures that this main function is called when we run the script from our terminal with the command python main.py. That's it. All of our complex logic is neatly encapsulated in our trainer, and our main script is just a clean, simple launcher. And with that, our training process is complete. Let's take a moment to step back and appreciate the incredible state-of-the-art system that you have just built. This was a true deep dive, and you've accomplished a tremendous amount. We started our journey with a deep dive into the theory of AI alignment, tracing the evolution of fine-tuning from the early days of supervised fine-tuning through the complexities of RLHF and all the way to the modern and efficient DPO and ORPO algorithms. Then, we rolled up our sleeves and did what very few tutorials do. We built a complete LLMA model from absolute scratch. You implemented every single advanced component from RMSNorm and rotary positional embeddings to grouped query attention, giving you a fundamental understanding of this powerful architecture. Finally, we brought it all together. We created a professional end-to-end training pipeline that automatically downloads our data and pre-trained model. And we successfully fine-tuned our from-scratch Llama using the elegant and powerful ORPO loss function. You now have a deep practical understanding of how modern language models are built and aligned. The learning doesn't have to stop here. I highly encourage you to take this project and make it your own. Go into the config.py file and experiment with the hyperparameters. See for yourself how changing the alpha ORPO value affects the model's final performance. Try finding a new preference dataset on the Hugging Face Hub and fine-tune this model to be a specialist in a domain you're passionate about. And for a fantastic next step, you could build an inference, PyScript, and a Gradio web interface to easily chat with and showcase your newly fine-tuned model. If you've enjoyed this deep dive masterclass and you feel like you've leveled up your AI engineering skills, it would mean the world to me if you could take a second to like this video and subscribe to the channel. Your support is what allows me to create more free, in-depth tutorials just like this one, and it lets me know that this content is valuable to you. Also, be sure to share it with any friends or colleagues who you think would find it useful. Thank you so much for joining me on this incredible journey. Happy coding, and I'll see you in the next video.